Hey there, guess who's back? Now we're going to talk about periodic trends and what those are. So, there are certain things that influence atoms that we need to know, which include the ionization energy, electron affinity, their size. All these factors have to do with how strongly they're going to bond with other elements and what type of bond they're going to have. So, first, what types of bonds are there? Remember, there are covalent bonds and ionic bonds. Remember what they are? Covalent bonds are, like in the layman's terms, when two nonmetals bond, and ionic bonds are when two ions bond, which can be metals and nonmetals, or it can be a metal and a covalent bond, because sometimes covalent bonds end up being ionic. And then there's metallic bonds. We'll talk about those later. Those are different. Anyways, what actually are these? So when I say covalent, I'm actually lying, and so is your textbook. There's two types of bonds that are covalent, and the truth is, these aren't actually different bonds, they're on a spectrum. So, here's the spectrum. Metallics, we're not going to include. There are three sections. There are these two sections, which are what we call the covalent bonds, and then this section, which is the ionic section. And what this spectrum is how polar an atom is. Covalent bonds. Now, polarity, if you remember what it means, is to have two ends that are different from each other. And this is going to be more polar, and this is going to be less polar. Let's use an example. Say I have an atom, or magnet, you could say magnet too, and divide it in half. I have two halves. Let's say they are both equally charged. So I have little plus, little plus. This is not a polar bond. Polar ends are going to repel each other. Let's say that this end is plus and this end is negative. This means they're going to be opposites. This is a polar bond when the two ends are opposite. Now, in an ionic bond, this would be our covalent, this would be our metal, and this would be our nonmetal. Why is this? It's because the metals are willing to donate electrons, and the nonmetals are willing to take electrons from the metals. That's why they bond, because they share electrons. And it's electric because of that. And we prefer to think about the electric side. Now, electrons are mass and they have a field, which means that your cation side, the field around it of like whatever is going to be small, because the negatively charged end is taking all the electrons. So the field of positive end is going to be much smaller than the negative end. Now, the strength, or the location on the spectrum, I mean, depends on the magnitude of these two values. So if I have, divided into two again, if I have really big negative down here, like let's make that thick, and a really big positive over here, there's going to be a lot of force pushing them apart. So this end is going to be really polar from that end. It's going to be a really strong ionic bond. Well, I mean, they're going to be very distinct. They're not going to be pushing away from each other. They're going to be attracted very, very forcefully. And that's what's holding them together. It's the positive and the negative attracting to each other. And yeah, so it's going to be very, very negative and very, very positive. Now, the opposite is also true. When you have a very little negative and a very little positive, you're going to have a very weak bond. It's still technically going to be polar. Like, this end is going to be slightly positive, this is going to be slightly negative, but it's not really going to be enough to say, like, oh, that's strong. This is what a covalent bond is. Covalent bonds are really, really weak ionic bonds, and they're held together by other things. Actually, they're just held together by that. They just hold themselves together, but they're very weak in that sense. Yeah. So covalent bonds are strong for a different reason that I can't remember, but I'm gonna have to review. So the weakest are gonna fall into here. The middles are gonna be this and then there. So this section is gonna be the nonpolar covalent. This is gonna be polar, and this is gonna be ionic. The threshold for this is determined by the periodic trend. There are two qualities atoms have that determine how strongly they're going to attract to each other, which is the electronegativity and the electron affinity. These are essentially the same term in concept, but mean different things. So electronegativity refers to how much energy you have to pour into an atom for it to like give off an electron. I'm pretty sure it was that. Yeah, to remove an electron to create a cation. And electron affinity is the energy released when an electron is added to a neutral atom to form an anion. So what this means is that elements with really high electronegativity are going to, no, that's not it. Sorry, I was wrong. Dang, this is the hole that I have in my knowledge. But how do you know where it falls on the spectrum? It's by the difference in electronegativity between two elements. For example, let's say hydrogen has an electronegativity of 1. It does not, but I'm using this for an example. Let's say fluorine has an electronegativity of 5, and chlorine has an electronegativity of 4. So, the higher the difference, or the greater the difference in our electronegativities between two bonded things, so we're going to end up with hydrofluoride and hydrochloride, or hydrochloric acid and hydrofluoric acid, the difference between how strongly they're held together is going to be the difference in electronegativity, actually. So, if I subtract, or the distance between 5 and 1, which are the electronegativities, is 4, so delta 4. The difference between chlorine and hydrogen is delta 3. This means that since it's bigger in between hydrogen and fluorine, that our fluorine is going to be more ionic and more strongly held together than hydrochloric acid, HCl over here. They're going to be different because the more similar two elements are in electronegativity, the weaker their ionic bond is going to be, and the less polarized they're going to be. An ionic bond is just a very, very polar molecule, and a nonpolar, barely anything. So, that is one of the trends. Now, how do we predict this trend? I'm going to draw a periodic table. Six. Okay, so here's our periodic table. Now, mass is the first trend that we have to think about. Atomic mass increases as you just go boom, boom. So as you go down and as you go this way, which means the highest mass is going to be right here and the lowest mass is going to be right here. Now, we have to consider the radius, how big it is. The size of an atom is going to determine, or size of a molecule, atom is going to determine how it demonstrates certain characteristics. So, atom size increases as you go down, but the magnitude of attraction, or atom mass increases as you go down, but atom attraction increases as you go this way. Why is this? Because they have more protons as you get to this side of the periodic table, and more electrons in their shells. This means that as you go this way, even though your mass is going up as you go down, which technically increases the size, the contraction of that atom is going to be higher over here, which is why this atomic radius of like francium, which is the one that's on the bottom corner, is going to be huge. Meanwhile, when you get up to fluorine, it's going to be absolutely tiny. And in addition, whatever this one is, probably has a weird name like Darmstadtium, is also going to be pretty small, especially compared to that end. It's going to be bigger than the one that is in its group. It's going to be bigger than the previous ones in the group, but it's going to be smaller even maybe than ones that are up here, that are higher on the table, but further to the left. So that's our first trend, the trend of size, or atomic radius. So the atomic size is going to decrease as you go that direction. Now, this is going to be the inverse of a lot of things, which is going to make it pretty easy to remember. First is electronegativity. Electronegativity, I'm going to draw in purple. Atomic radius. Atomic radius, that's the color. Now it's time for electronegativity. So electronegativity is going to increase as you go this direction, with the least electronegative being francium and the most electronegative being fluorine. We do not count the noble gases. Electron affinity. Electron affinity. My notes say that it goes up in that direction. I think those are the trends. Yeah, so electron affinity. Electron affinity also goes up. So it's like more likely to pull an electron to itself, and it's going to also take more energy for electrons to be freed. So what this means is you can kind of predict what elements will be more strongly bonded than others. For example, if they're farther apart on this, like if I have one that's like right here and up here, this one is going to be more electronegative than this one. If I have this one here and this one here, this one is going to be more electronegative than that one. And so as you go up and to the right, more electronegative, stronger, whatever it is. So the 4 most electronegative elements, I remember them like this. Fackeln. F, O, Cl, and N. Fluorine, oxygen, chlorine, and nitrogen. In order, those are the most electronegative elements. And they're going to be important later on when we talk about intermolecular forces and some other stuff. But for now, you can know that these are the most electronegative elements, which means they will form the strongest ionic compounds. I'm going to pause. Okay, first, quick note on valence electrons before I forget. You can know what ionic charge an element is going to have based on how many it needs to have a full subshell. For example, the charge, not valence electrons. So you have a certain amount of valence electrons, and what an element wants is to get to a level where it either has all its valence electrons or none of its valence electrons. So take, for example, oxygen, which is in period 16. It has 6 valence electrons. To get to a full octet, is going to need 2 more, which is why oxygen has a charge of -2, because it's going to take on 2 electrons when it bonds with something. And the same goes for here. Say sodium has 1 valence electron. The easiest course of action is to lose a valence electron to get to its stable level. That's how you know. Just quick aside. I'm going to pause again. Okay, more notes on ionization energy. So the the meaning of ionization energy is like the amount of energy required to make an ion. So like if you want to make an anion, you have to add energy, and to make a cation, you have to yeah, you have to like oh yeah, a cation. What a cation does is it flings an electron out, so it makes more positive. You have to add energy to get a cation. Subtract, and then when you give an electron, it releases energy, which is like a subtraction of energy. And yeah, so what that means is that for our ions, they're going to have different ionization energy than their individual elements. For example, oxygen. Oxygen is going to be right there. So let's say we have an oxygen ion, and it's going to have -1. What this means is that its ionization energy is going to be significantly less because we only need to add a tiny bit to get that ion or that electron fly off again. Now, if let's say I had O plus, O plus is already electron deficient. It's already missing an electron. So if I wanted to make a further cation, I have to add an incredible amount of energy just to get that other electron to just be like, bye bye, I'm leaving now. Anyways, that's my quick note. Ionization energy is the amount of energy required to form a cation, which means that cations will have a harder time, will have lower that. Yeah, so that's why ionization energy increases as it goes this way, because these are electron efficient, not deficient. So they can hold it. All right, now let's talk about ionic radii. So first, I'm going to be like ionization energy and electron affinity are in purple, but ionic radius is not the same as atomic radius. Ionic radius. So ionic radius is actually dependent on how many electrons and protons you have generally. Within groups, it will just descend down. So that's because you're adding on shells. So if I have helium, its ionic radius is going to be small, and we're assuming it's an ion in this moment. Lithium is going to be bigger because it has another shell. Uh, Sodium is going to be even bigger than the other two because it has another shell, and it's going to keep going down like that until you don't have any more elements to get bigger with. But when you're going side to side, it's going to be the one that has fewer protons versus electrons. This is because uh, the the more protons to electrons you have, the more an atom is going to contract. It's going to go because the forces working within it, the positive and the negative, the polar sides, are going to attract each other with more and more strength. So this means that up here, you're going to have a really small ionic radius because you have a lot of electrons. And yeah, so when you have the same amount of electrons in an element, it's going to depend on how many protons you have. So when you have the same electronic configuration between ions, just referring back to this, uh, ionic radius, oh, it's in the question. Yeah, ionic radii will increase down a group. Yeah, so the smaller ones are going to be at the top. Hold on, that fell. Yeah, so it's going to increase down because you're adding on shells, but they have the same amount of valence electrons. Meanwhile, compound or ions that have the same charge, like Al3, Mg2, and Na, are going to have the same number of electrons, but the one with the fewest protons will be the largest because it's not being held together as strongly. That's what it is. So they all have the same electrons, and you compare it like a graph, like, oh, I have 3 electrons. Oh, I have 5 electrons. Easy. I have 1 electron. So if we all have the same amount of protons, or different amounts of protons, yeah, let's say these are the protons, and we all have 5 electrons, Which one is going to hold itself together stronger? Is it going to be the one that only has 5 to 1, or is it going to be the 5 to 5? It's going to be this one because it has 5 little bonds in there. Meanwhile, this one has 1, and this is going to have 1, 2, 3. So the one with more protons is going to be stronger because or going to be smaller. Double check it with a question. Yeah, fewest protons will be the largest, more protons will be smaller because it's contracting more. And that's it. I think that's about it for our periodic trends. I'm just reviewing the chapter material and homework to see if I can answer all the questions. Cool. Well, it looks like that's going to be it for this video. I finished everything. All the material for chapter 6. Now it's time to move on to chapter 7. And it's only 9 o'clock, so we got time.